Hello everyone, my name is Andrew Kim and welcome to my 5th video of the AP Physics 1 review session. So if you finished up to video 4, then I believe that it's a good moment to learn about momentum in Unit 5. So let's get started right away. So first of all, what is momentum? Well, as a Korean, in Korean, momentum means exercise amount. We call it exercise amount, and I believe that this is a great definition because momentum is basically about how much of exercise is this object doing. And in terms of equation, momentum is equal to mv, or mass times velocity. Now think about it. If you have a huge fat person running at a velocity of v, of course the amount of velocity he is doing amount of exercise he is doing would be greater than a skinny small person running at the same velocity. Why? Because this person is fatter, because this person has more mass. Thus, if they're moving at the same velocity, of course the amount of exercise this person, the fat person, is doing would be greater. Thus, momentum is greater. Now, if both people are skinny, but one person is running at a velocity of v and the other person is running at a velocity of 2v, of course, the momentum of the person above who's running faster would be greater because this person would be doing more exercise. The exercise amount of this person is greater. This is why I believe momentum, the best way to describe momentum is the exercise amount that a person or an object is doing. And again, the formula for momentum is mass times velocity. If the mass is greater, higher momentum. If the velocity is higher, higher velocity. Now, let's think about impulse. Again, in Korean, impulse, you call it shock amount. How much of shock is given to a certain object. So, and in terms of equation, impulse is equal to delta p, or the change in momentum, over delta t, or the change in time. Why? Well, think about it. If the momentum or the exercise amount changes abruptly, changes shortly, there will be more shock. Think about it. A person is running and he in right direction at a velocity of v, and then he suddenly stops and his velocity changes to 0 in a very short time, in 0.0001 second. This person will feel a lot of shock because he was running so fast and then he instantaneously just stops. So greater shock amount, greater impulse, because lower delta t, lower change in time. Also, same logic. If two people stop instantaneously at 0.0001 second, but one person stops when he was stopped from a velocity of 2v to 0, and the other person stops from a velocity of v to 0, of course the amount of shock that this person feels will be greater when he's moving faster. Because if you're moving faster, and then you instantaneously stop, of course the amount of shock that you feel will be greater. Thus, greater change in momentum, meaning that greater change in impulse. So it's easy if you think about the shock amount of the object. Or in terms of equation, again, you can express it as I, or impulse, equals to delta p over delta t, which is also equal to delta mv, because p is equal to mv, so you can substitute mv inside p over delta t. So that is what you get. That's what impulse is, and that is what momentum is. Now, this formula, impulse, actually explains us why it hurts less if you fall on a sponge or a matrix instead of falling on a wooden floor. Because think about it, if you fall on a wooden floor, delta t is going to be really short. Because if it's a wooden floor, it's stiff. You're just gonna fall onto it and your velocity will instantaneously drop to 0. Whereas if you fall on a sponge, you're not just gonna instantaneously stop to a velocity of 0, but you're going to actually push the sponge in and still move for a given amount of time. So the time that it takes for your velocity to stop into 0 will be greater. Delta t will be greater. Thus, since the denominator is greater, the fraction or the impulse would be smaller. impulse is smaller, the shock amount is smaller, meaning that you would feel less, it would hurt less if you fall onto a sponge than a hard rock or wooden floor. So that's one thing you can see over here. Now, let's move on to the next concept, which is the conservation of momentum. Now, similar to the conservation of energy, the momentum conserves on a closed system. Now, what's important is if you look at the formula of momentum, you can see how m, the mass, is a scalar, but v is a vector. Always, if you multiply a scalar to a vector, like F equals to ma, where m is a mass, it's a scalar, and a is acceleration, a vector, then the result, the product of the two, should be a vector. Same idea. P is equal to mv, momentum is equal to a scalar times vector, meaning that the momentum, or the product of the two, should be the vector, a vector. So the momentum would also have direction because it's a vector. Now, the reason why I talked about this is because when you say momentum is conserved, it doesn't simply mean that the multiplication, the product of m and v should be constant, but it also means that the direction where the objects are moving, or the direction of the momentum, should conserve as well. For example, let's say you have two marbles on a floor. One is moving at 5 meters per second. This one's just staying still. Two collides, and then they start moving together. Now, it's not only important. So it's not only important to remember that the momentum of the combination of the two marble will still have the same value as 5 times whatever the mass is. Let's say the mass of this block is I don't know, like 5 kg. Then the momentum of this ball, the initial momentum, would be 25 kg times meters per second. But now, what's important is that it's not only important to remember that the momentum of the combination would still be 25, but it's also important to remember that the direction of the two balls will be moving towards the same as initial, which is rightward. Because, or else, some people might say, yes, I get that the two ball would move on the momentum of 25, but we don't know which direction. Does it move left? Does it move upward? Does it move down? Well, obviously, it would continue on the direction of the initial momentum, which is rightward. So just keep in mind of that. Now, when it's just on a 1D plane, on a line, this is very easy to see. However, once you move on to a 3 or 2D plane, where you have x and y, vertical and horizontal axis, things might get more complicated. What if this one marble hits the two marbles and causes the two marbles to move? What would be the momentum? How would the momentum be conserved in which direction? Now you would have to evaluate those things smartly. So that's all about momentum conserved. And what's important is that when you get a question that's related to momentum, you can't just assume that the energy will be conserved. Energy does conserve if you look at the system as a whole, but if you only look at the individual marbles, again, the energy might change. Thus, it's impossible to use energy conservation when you're solving a momentum problem. When you're solving a momentum problem, you would have to use the conservation of momentum, not the conservation of energy. However, there is a rare case where you can actually use the conservation of energy as well, and that is a situation when the two marbles or two objects are colliding in an elastic collision. Now, in order to explain this, I'll first talk about the difference between elastic and inelastic collision. Elastic collision is, again, a collision where the energy also gets conserved. So that's literally the definition. And as the word tells you, it's elastic. They bump and they spread out. In contrast, inelastic collision is a collision where energy does not conserve, and this is a more practical collision. And majority of the collisions, the energy will not conserve. Not majority, but in fact, in real life, every single collisions won't have energy conserved. It will be inelastic. For example, we can think about a bullet. Let's say a bullet is flying towards a box. would the bullet just bump towards the box and move towards a different direction? Would the collision be elastic? Of course not. The bullet will going to actually go through the box and we're going to stop in the middle of the box and the two objects will move together. It's not going to be elastic. One is going to stick to the other and just move together. So there are these types of inelastic situations where energy does not conserve, and again, in real life, every collision is inelastic. But if the question specifically mentions that the collision is elastic, that means that you can also use the energy conservation, or else when you solve a conservation of momentum problem, you should only use the conservation of momentum to solve the problem. Now, I think I explained things well, but I didn't really show how it can come out in question. So I'm going to give you an example scenario. Let's say you have a ball that's 2 kg and another ball that's only 1 kg. Now this ball is moving initially at a velocity of 5 meters per second. Now, after the collision, the 2 kg ball moves upward 45 degrees and the 1 kg ball moves downward 45 degrees. If you're given such situation, how can you use conservation of momentum? Well, conservation means nothing changed. In other words, initial and final value should be the same. Now, what is the initial value, or what is the initial momentum? Well, initial momentum would be 2 times 5 because it's mass times velocity, which is 10. Now, after the collision, the ball moves upward at a velocity that we do not know yet. Let's say this velocity is v1. Now, let's think about the second ball. What was the initial momentum of the second ball? Well, it was 0 because yes, it had mass, but it had no velocity. And since momentum is the product of the two, if there's no velocity, the momentum of the second ball would be 0. However, after the collision, this ball will move downward 45 degrees at a velocity, unknown velocity. Let's say that the unknown velocity is v2. Now, what's interesting is that, again, since velocity is a vector, it's always good to actually split the vector into x and y component. Now, what you can see is that the initial momentum that was present was only in the rightward direction. There was no momentum in y-axis direction, meaning that in the final momentum, also, there should be no y or vertical momentum present, meaning that this component and this component of the momentum should cancel out. Thus, this component and this component should be the same. Same magnitude, but different opposite direction so that they can cancel out. Now, what is the value of this component? Well, first of all, the total conservation of the first ball after the collision would be m times, or m would be 2 kg for this ball, 2 times v1. But this component specifically would be 2 times v1 times cosine 45, because you have 45 over here. And that would be 45 over here as well. So cosine 45. Now, using the same logic, we can figure out that this component of momentum of the second ball after the collision would be mass times velocity times 45 cosine 45. Now, we know that these two are only magnitudes, so they should be the same while having the complete opposite direction in order to cancel out and leave 0 vertical momentum, which is because initially you had 0 vertical momentum, and the momentum should conserve not only as magnitude but also with direction, because momentum is a vector again. Thus, you can make an equation that v2 cosine 45 equals to 2v1 cosine 45. You can cancel out cosine 45 from both sides, which give you that v2 is literally equal to 2v1. v1 will be the half of value of v2. So instead of v2 over here, you can substitute 2v1 inside. Now what you can do is that you can look at the horizontal component. Now, if you think about the horizontal momentum, the initial horizontal momentum was 5 times 2, 10. Now, momentum conserves, thus the final momentum of the two balls, the sum of the final horizontal momentum of the two balls should also be 10. Now, the horizontal momentum of the first ball, the 2 kg ball, after the collision would be again mass times velocity times cosine 45. And the horizontal component of the momentum of the 1 kg ball after the collision would be mass times velocity times cosine 45, because 45 degrees. Now, you know that V2 is equal to 2V1, so you can substitute that in, which would give you 2V1 times cosine 45. Now, if you add the two, that would be 2V1 cosine 45 plus, again, 2V1 cosine 45 equals to 4V1 cosine 45, which is 2 square root of 2V1, and that should be equal to the initial horizontal momentum, which is 10. Thus, V1 equals to 2 under 5 square root of 2. Ta-da! And if you know V1, you can substitute the value inside here to calculate V2, which would be 5 square root of 2. This is how you would solve a momentum problem. Now what's interesting is, now let's check if the energy is conserved or not. Well, if you think about it, initially, the energy present was the kinetic energy, and that could be calculated by 1/2 mv squared, and that is 1/2 times 2 times 25, which is 25. You had 25 joule of kinetic energy present initially. Now, after the collision, in the final state, well, you would still only have kinetic energy present. And the kinetic energy of the first ball will be, again, 1/2 times mass times v squared, which is v1 squared, which is 25 times 2 over 4, which is 1/2 25, the half of 25. Now, if you calculate the kinetic energy of the second ball, that will again be 1/2 mass times the square of velocity, which would be 50. If you calculate this, you can realize that that's 25. Now, what's interesting is that if you add the two, you can see how the energy is in fact greater than 25. The energy changed. So there should have been some additional force or something applied onto the system that actually increased the energy present. So again, the lesson here is that unless the question tells you that the energy conserves, or unless the question tells you that it's an elastic collision, you have to assume that the energy does not conserve and only use the momentum, the conservation of momentum, to solve the problem. And also, when you use the conservation of momentum, again, you should always keep in mind that momentum is a vector and its direction should also be conserved. Not only the magnitude, but the direction. And when you say direction, it means horizontal or vertical direction. When it initially only had vertical momentum, that in the final state, also, there should only be vertical momentum, and there shouldn't be any the other direction momentum present. So they should cancel out in this case. So that's how you would solve momentum-related questions. I hope this made sense. Thank you for listening to my review session, and don't forget to have a great day.